Welcome. Today we want to talk a little bit about the more practical aspects of creating semiconductor materials and in general crystalline materials, and how we create all these types of devices that we've been talking about in the last few sessions. So this is, although this will be just a theoretical class, we will really discuss very practical aspects of the manufacture of these materials. So I will be referring mainly to silicon because it's the most used semiconductor. However, many of these techniques can have, with slight variations, can be applied to other semiconducting materials. Okay, so how do we produce silicon? The silicon that we then use to produce, for example, integrated circuits or photodetectors or any other semiconducting device. And the answer is, well, the first thing we have to obtain is silicon. Silicon, I don't mean crystalline silicon, but just the silicon material, even in other less appropriate forms. And the process starts with sand from the desert. I mean, the desert, the Sahara Desert, for example, contains mostly silicon oxide. So sand is basically silicon oxide with some organic impurities and other things. So one can apply, one can wash these, collect sand, wash it with water and other things, or even use some acids or other chemical processes just to get rid of all these pollutants that come with sand, and end up with just basically grains of silicon oxide, which still have some impurities. Then from the silicon oxide we have to remove the oxygen, and that process is achieved by mixing the silicon oxide, or this more or less cleaned sand, with carbon, and then heat it up to high temperature, about 1,000 degrees or so. And this process, this produces a chemical reaction in which carbon monoxide is produced. So the oxygen goes binds to the carbon, and we end up with amorphous silicon. So we get silicon which is not super high purity, but is reasonably good purity. But it's not a crystal. It's just silicon in a polymorphous material. And subsequently the preparation of the crystal really is when it starts. So these silicon can be further purified by mixing it with hydrochloric acid and a few other chemical steps, just to get it really clean and so on, and get polycrystal powder. Basically it's just powder or granules, which are really the raw material that is then used to create monocrystalline silicon. Right, so once you have this material, which has already undergone all these complicated chemical cleaning, so to speak, what we do is we put this silicon in a container which can be heated up to relatively high temperatures. So let's see, it's not looking very nice. Right, so we have this crucible, this is just a container that can withstand very high temperatures, and we put all these powder or granules of silicon in there. So we put all these granules, we heat it up to over 1,000 degrees, something like 1,200 or 500 or so, I don't remember the exact temperature. And at some point these silicon powder melts. So what you end up is with a liquid that is very high temperature. And the next step is basically implies, first of all, well, we have a rod here, which is usually a metallic rod of some kind, which is attached to a motor that can rotate, and also another motor that can bring it up and down with high control of the rotation speed and the speed of pulling and so on. So we can control the position of this rod very precisely, and and move it with a high degree of control, so to speak. Okay, the next step is in this rod we put what we call a seed, and a seed is crystalline silicon. So it's a small piece of crystalline silicon, something like a grain of salt, or maybe a little bit bigger, but it's a relatively small piece of very high purity, very good quality, single crystal silicon. Okay, and I will try to make a drawing here and move. So I will try to make this bigger over here. And what we have there is this silicon crystal, this very high purity crystal, which, let's imagine, has its atoms aligned like this. So we can control and decide which ones, in which direction we put each one of the crystallographic directions. And the next step is we bring this seed down to the surface of the mold. So we bring the seed down to here. We put it in contact with the so the rod goes all the way down to here. We put it in contact with the surface of this liquid silicon, and what happens is the seed is at lower temperature, and the metallic rod essentially can conduct heat. So the rod more or less maintains although the seed heats up, it keeps heat flowing, and therefore what happens is that the atoms of the liquid silicon, I will draw the liquid silicon on this side as well. The atoms that are really close to the walls of this silicon seed. So this is again, this is the rod that can be pulled up and turned around and so on. All the atoms that start lowering its temperature in the mold, in this liquid that is around the seed, start adhering to the surface of the silicon seed. So since this is at lower temperature, they adhere and they solidify, but they solidify in such a way that they follow the same crystallographic orientation. So if atoms were aligned in these directions, for example, the next layer of atoms that now adheres to the seed follows the same crystal structure, and so this thing starts growing and growing, and you start. I mean, if we control the rotation speed and the pooling and so on, all of that is just to keep the thermal equilibrium and start pulling slowly the seed out. What we will find is that the seed starts growing. I mean, a crystal starts growing around the seed. So what we obtain is something that, so we had the original seed here, and now the crystal starts growing like that, okay? And by controlling, again, the rotation speeds, and so the rod is somewhere around here, and it's, again, rotating and pulling, and let's say the mold level is somewhere around here. By controlling the pulling, so the speed in which we pull the seed out and also in which we rotate it, we can control how big this thing gets. So we can more or less control the diameter of this thing that we will call the ingot of silicon. And again, heat keeps flowing, so the ingot is at lower temperature, of course, than the mold, and the mold keeps adhering to the ingot. So we can keep pulling and pulling and pulling, and at some point, what we end up with is, I mean, eventually we will run out of material. So if we see this, eventually we will have just very little material, and what we will have is the original seed will be something like that. And then we will have the ingot that is going to be something that looks a little bit like a cylinder there, which is a large, very long single crystal of silicon. Okay, this process, there are variations around it. Of course, all of these processes is done in an inert atmosphere, so oxygen free and so on. So all this is done in a furnace that is in the absence of oxygen or other materials that can produce chemical reactions with the very hot silicon. And what one ends up with is a big, long single crystal of silicon that is super, super high purity. I mean, people who know how to do this, and again, I'm not a crystal grower myself, but people who know how to do this, they obtain the degrees of purity that this crystal can achieve are extraordinary. And it's not just chemical purity, but in terms of defects as well. I mean, it's a single crystal that has less than one defect per million atoms of silicon. Actually, I think germanium is the semiconductor that can be grown with the highest the lowest degree of defects. And basically, you have something like there are people that can grow germanium with only 1 or 2 defects per cubic meter of material, which is really amazing. I mean, you really have large pieces of material that can be completely defect-free or almost completely defect-free. So these ingots can be grown in several different sizes. Typical diameters go from around 1 inch, so about 25 millimeters or so, to about 100 millimeters or 300 millimeters are the largest one. So 300 millimeters is about that big. And all these ingots they're really big pieces of semiconductor, a single crystal, as I said. And by, again, using very pure silicon, one can produce intrinsic, very high resistivity silicon, but one can also, on purpose, add the dopants into the mix. So when you melt the silicon, you can add a controlled amount of group 3 or group 3 or group 5 materials in order to make the material p-type or n-type, and not just p-type or n-type, but really control how many carriers per cubic meter or per cubic centimeter one introduces into the ingot. So one can have really extraordinary control over the electrical properties of the material that comes out. So here I include a photograph that I took from Wikipedia of an ingot, which is basically this big rod. It's really big chunk of material. Here one can see where the seed used to stand, and you have this really long rod of high purity silicon. It's a single crystal, so all of the atoms in all these really big chunky piece of silicon are actually aligned to each other in the crystallographic direction. So it's very large macroscopic material. And basically the next step in order to be able to use these for integrated circuits or for manufacturing any other electronic or optoelectronic device is basically slicing it. So using a saw, not a normal hand saw, but special saws that are made with diamond powder, one can slice these ingots transversely. So the ingot is sawed like that in very thin slices. Slices are typically somewhere between 50 and 300 microns, although you can find them in other thicknesses. And these thin slices are called wafers. They look like this, and essentially on top of these wafers, which they are cut very carefully so that one is following one of the crystallographic directions, and therefore the surface is in one of the crystallographic planes. And after sawing, the surface is polished and brought down to basically a really super flat degree, which is as much as possible aligned with the crystallographic direction. So basically, this plane that you see here is a crystallographic plane, and on these wafers are the base of our modern technology. So these wafers are where we start building up our electronic and optoelectronic devices. In addition to the methods used for bulk growth that are all variations, as I've already said, of this idea that I just gave you of melting the material and then growing around a seed. There's another, let's say, family of methods that can be used for growth of more complicated structures. And these methods are very useful when you want to grow interfaces or complicated systems that contain many layers, in which you can combine different doping levels or even different materials with different band gaps and so on. And these are called epitaxial methods. Probably the best crystals that can be grown at the moment by mankind are grown by a method that is called MBE. I will put it down here, MBE, which stands for molecular beam epitaxy. Essentially, the MBE method is consistent of the following. We usually start with a wafer. So you start with a wafer that was grown by one of the bulk methods. This wafer is put in a vacuum chamber. So let's just draw here a vacuum chamber. And this vacuum chamber is actually a very good vacuum chamber. So the amount of gases that are still dispersed there is really very small. It's some of the best vacuum chambers that can be produced are used in this type of growth. And then depending on the semiconductor or the different semiconductors that you want to grow, you put a series of little furnaces that are little containers that you can heat up electrically. So you have a collection. I will just draw 4, but you can have more of these containers where you can put different materials. You can put I'll just put some for the sake of it. So for example, silicon, germanium, gallium, arsenic, just to put some. Okay, this could be the main components of your semiconductor. So for example, if it's a silicon wafer and we want to keep growing silicon, then we will have, of course, a silicon furnace there, or a silicon source, and we can have different dopants, gallium and arsenic, for example, which are 3 elements from the group 3 and 5, for example, but they could be many. Okay, so the idea is that these containers can be heated up with electrical resistors that are controlled from the outside to very good degree of precision, so we can heat them up very precisely to the point that we can evaporate all these materials. So we can start producing silicon vapor or germanium vapor or gallium or arsenic. These usually also have a shutter that can be open or closed from the outside, so that we can control very accurately the flow of gas, of atoms that are evaporating from there. And the idea is that with these materials we can produce beams of molecules or atoms that basically are sent onto the surface of the wafer, and the wafer is also heated up. So it's heated up to a certain degree, not enough to melt it or evaporate it, but just to keep the lattice vibrating a little bit. This will help with the growth of the crystals, and these sources basically send atoms in this gas form. It's basically just really a beam of atoms of silicon or germanium or gallium or arsenic or whatever you're using in your growth. And the idea is that if the correct conditions are given, and this is the correct temperature of the wafer, and also the wafer is usually rotated so that all the surface is covered more or less evenly with these with the atoms that arrive and stick to it. And again, as I said, if we give the correct conditions, we can grow extraordinarily good quality crystals with this. The only problem is we can only grow thin layers. So layers are typically below 1 micron. So are a few nanometers, or a few tens or hundreds of nanometers, not to just a few microns. And the idea is that with these we can start making layers in which we can vary the chemical composition. By chemical composition, I could say, I mean, for example, you can use silicon and then put, in principle, let's say, a germanium layer and then back to silicon and so on. That is actually not possible, or it's very hard actually to do, and it's very hard just because the lattice, so the separation between the atoms of germanium, let's say, and the atoms of silicon in the lattice is different. So the spacing in the lattice is different, and therefore when you try to grow germanium on top of silicon, this could be hard just because the atoms don't align with each other, because they will be stressed. I mean, the layers near the interface will be either pushed together or far apart, depending on the mismatch between the two lattices. But let's not worry about the lattice mismatch yet. The idea is that in principle this can be done, and up to now this kind of growth can be controlled down to the single atomic layer, almost single atomic layer degree. So we can grow really very precisely, very precise thickness of these types of layers. And with this, let me move on to the next slide. If you think of your wafer, so I will put here a cross section of the wafer. So this is the initial bulk grown wafer. We could grow, for example, N or P doped layers, and for example alternate between P and N, and there I will produce, for example, a diode. If these two, I mean, if all these layers are silicon, but one is the green one here is for example N doped, and the yellow one here is P doped, then we create a big diode that can be as big as a full wafer, for example. And not just that, we could start actually, if we don't worry too much at the moment for the lattice mismatch problem, which we will talk about a little bit more about in just a minute, we could even combine different semiconductors. So we could grow, for example, have a wafer of let's say gallium arsenide, and then grow on top a layer, for example, of indium arsenide, and gallium arsenide has a broad band gap. So the band gap is about 1.42 electron volts, and indium arsenide is much smaller. It's in the order of 0.3 electron volts. And we could, for example, grow another layer of gallium arsenide here, and if we then make a plot of the band gap as function of this position here, what we will find is that the band structure, or well, not the band structure, but the bands will look something like that. This is the this here is the 0.3 electron volts, and this is the indium arsenide layer here, while this here is the 1.42 electron volts, and this is the gallium and gallium arsenide layers. And with this, as we mentioned in one of the lectures earlier, it is possible to create this type of potential wells. So if you look at these energy restrictions, it so happens that this looks this area over here, this area that is right here, looks exactly like one of the square wells that we discussed at the beginning of the course. So these square wells are not just an academic abstract system. They're actually something that we can make, and by making these kind of wells, we can by deciding the energy, the width, the width of this well, so how much material we grow here, if it's 1 micron or 1 nanometer or 100 nanometers or whatever, we can do, so to speak, quantum engineering. We can make a quantum system which will have energy levels spaced by a variable that we can control when growing the crystal. So this opens extraordinary possibilities, in the sense that we are now able to create quantum systems that have a spacing between their levels in whichever energy we want, in principle. And these kinds of systems do exist. So a real-world example of these type of structures is this article from a little bit over 10 years ago. This structure shows actually the wells. So here you can see how the barriers are. I'll just try to draw them a little bit more. So you see there is a well here and another well, and the barriers in between, and so on. This was a structure that was fabricated with aluminum gallium arsenide, which is a ternary semiconductor, and so on. So I'll just leave it there. And this structure was engineered in such a way that when you apply a bias, and that's why the wells look a little bit tilted, the levels would align in such a way that it would produce a cascade of optical transitions. So it produces many photons in the process of, an electron that passes through this complicated structure produces many photons. So that's what is called a quantum cascade laser. And not only that, it's a quantum cascade laser that produces photons in the very far infrared. It's a region in which we don't really have any materials that can properly produce radiation, because the distance between the levels is so small that it's very hard to find the correct materials. But with these complicated series of wells, which were repeated many times, one produces a series of wave functions, which are also there in different colors, in blue and red and so on. And wave functions are such that their overlap and the separation between their energies and everything is appropriate to start to produce this cascade of photon emissions and produce photons in this region of the spectrum, which was or still is somewhat very difficult to access. So this is an actual example of how we can do real quantum engineering and produce systems that solve problems that we have in real life by just tweaking the levels and designing structures such that you produce the correct quantum levels for in this case the production of photons, but for many other applications. In principle, you could produce sensors, you could produce all sorts of different devices that benefit from the fact that we can now place the quantum levels where we want them by just tweaking the thickness of the wells and the barriers in between these wells, which we can grow by these epitaxial methods. Okay, so there is, apart from MBE, the molecular beam epitaxy method, which we just briefly discussed, which is, by the way, the method that produces the very best crystals that we can produce, but also is a very, very expensive method, and it's very, very slow. So we really are depositing the atoms almost atomic layer by atomic layer, and this makes it very, very slow, extremely expensive. One of these, an MBE machine costs of the order of $1 million, and it could be more or less, a little bit more or less, but we're talking about really, really very expensive equipment. And not just that, running it, I mean, keeping this machine running and producing is something that requires people with a lot of training, very, very specialized training, many, many years of experience, and so on. So it's a method that is, first of all, very slow, so it's not really compatible with industrial processes. I mean, this is great for research purposes, and here in the university there is at least one MBE reactor, but there are I mean, in general, in research facilities, you can find these kinds of equipment, but they are, as I said, they are very hard to run. They are not very efficient in terms of time. So growing one of these structures of many wells on top of a single wafer might take days of work, and so it really is not compatible with industrial processes. And not just that, the fact that it's so expensive also makes it incompatible with many small laboratories or small groups that don't have the access to this type of funding. So there are alternatives which are more compatible with lower budgets and also more compatible with the timescales of industrial production. And this other technique, I will talk just about one, and the others are basically roughly variations that go around this one. It's called MOCVD, and that stands for metal, organic, chemical, vapor deposition. And this technique is in principle similar in the sense that it's also an epitaxial technique, just like MBE. However, the way the crystal is grown is very different. So we start with a wafer. So again, a wafer grown with one of the bulk techniques. And this wafer is also put again in a vacuum chamber. But now this vacuum chamber has, for example, the access to pipes that you can control with valves that you can control very well to a few different gases. And these gases are typically gases that contain an organic radical. So it's typically something with carbons and hydrogens and so on. So it's basically a radical, and it has bound the element that you want to deposit. So, for example, gallium, or let's say another radical which we will call R prime, with arsenic, or whichever other atoms you want to deposit on top of the wafer in order to start growing these layers. And you can have, for example, a radical bound to a silicon or germanium or whatever other materials. So these are typically things that you can buy in gas form. They usually materials that are not very nice to have. So it's, I mean, there are safety concerns around this. But apart from that, again, you have the wafer rotating, and you keep it at reasonably high temperatures so that the atoms are vibrating, and this allows the atoms that come in to more or less move a little bit around and find a lattice site in which they can fit. Again, so the idea is you can very precisely with these electrically controlled valves very precisely let a little bit of these gases in. This is the exhaust, so here we have a vacuum pump that is extracting all the air and whatever else comes in. And what you typically have is that this let's say you want to grow gallium arsenide, so you want to put more or less the same amount of gallium and arsenic. So you let some of the gallium containing gas in here, some of the arsenic containing gas here, and these two gases tend to react, and basically the energy the energy of the reactions is such that the organic radicals tend to bind together and leave the gallium and the arsenic atom free. And this usually happens, well, it's made in such a way that this reaction happens near the surface of the wafer. So the gallium and arsenic atoms start locating on the lattice, on the surface of the wafer, and the rest, so these whatever results from the chemical reaction, so these are bound to R prime or a series of other organic compounds that usually are just the rest of the organic molecule that come with the gallium and the arsenic, are exhausted again as a gas that is just taken out of the chamber and disposed of. And this is something that can be done at much faster speed, so it's compatible, more compatible with industrial production. One of these reactors is also less demanding in terms of the quality of the vacuum and many other aspects. So some of these types of MOCVD machines can be found in smaller labs, in smaller research labs, and also are used in many industrial processes to produce layered structures. And just the same as you put gallium and arsenic, you could put dopants, so dopants that are bound to some organic radical. You can put fractions, or you can make alloys or ternary and quaternary materials with this. So this is essentially the way these kinds of materials can be grown in larger scales. And this is something that is used for many things. For example, for the production of LEDs, or for the production of photo detectors and many other devices that are very useful, that we have around us. laser diodes that are used, for example, in CD or DVD or Blu-ray machines, photodetectors that are used, for example, I don't know, in elevator doors to detect the presence of something. I mean, all sorts of different devices that can be grown and made by these methods. So, in summary, I mean, as I said, there are variations around this. You can add, for example, plasma here or a plasma generator in the reactor just to speed up or more or less catalyze the reactions that happen in the reactor or have a little bit more control over the reaction. But the idea is this in the end. So it's not all that different in the sense that you grow layer by layer. You can dope. You can make alloys. You can make complicated structures just like in MBE. It's just that it's faster and although the crystals are not quite as good in quality as the ones you can get from MBE. The truth is you can really do very, very well with one of these reactors, and this is the way many of the devices we use every day are made. Okay, so finally I just want to make a comment about the lattice mismatch. So let's assume that we have the wafer here, the original wafer. I'm just seeing at the cross section. And just for schematic purposes, let's assume that this is the top atomic layer. So this is the distance between the atoms. So in principle, we could start growing the same material. If it's silicon, let's say, we just keep putting silicon atoms on top. And the silicon atoms will tend to align with these ones and produce a nice lattice that just replicates the same lattice that we had below. So if we had this lattice below, the silicon will tend to just continue growing in the same exact crystallographic direction. And since this is the natural spacing between silicon atoms, all the lattice is relaxed, everything is okay. But if instead of growing silicon, we try to grow something different, let's say germanium, the interatomic distance for germanium might be a little bit different. So let's say that germanium has a more packed structure, just for the sake of the argument. Okay, so if it's dramatically different, what will happen is that all these atoms will, if I just zoom in here, all these atoms will really not align with each other, and the crystal that will be trying to grow on top will be completely mismatched. And what will happen is that these ones will, these atoms here will not really grow in the correct positions, and since they will not find a place to grow, these will start producing a horrible disorganized material in which the crystallinity is not very good, or even if we manage to make them align. So if instead of having something disorganized like this that I drew, you really force them to be at this distance instead of being at this distance. So we just find a way of not putting these atoms and forcing them to align with the silicon or the substrates lattice. What will happen is that these material that we grow on top, the yellow one, so the gallium or whatever it is, will be stressed. So it will be subjected to stress. This will change, of course, the lattice. This will change the band structure. It will produce also defects and all sorts of different things. So what we will get on top is not really germanium. It could be stressed germanium or germanium rich in defects and atoms not really aligning very well with each other and so on. And that is a problem. And people who do growing, I mean, I'm not a crystal grower myself, but but people who do growing is something that they are concerned with. And they have found collections of different materials that can be grown on top of each other, just because the lattice mismatch is so small, or is within certain tolerance, and so that for example, gallium arsenide and certain alloys of aluminum gallium arsenide, for example, can be grown on top of each other. And this is the way the quantum cascade laser that I just mentioned was grown, with gallium arsenide layers and aluminum gallium arsenide layers that are the basically the barriers are aluminum gallium arsenide, so some alloy fraction, and the wells are gallium arsenide. So with this in mind, one can know that only certain lattices will grow nicely on top of another. Yet, I mean, a lot of development has been done recently in the field of growth of semiconductors, and some tricks have been done in order to either preserve the lattice, although you still have some stress in the crystal that grows, or vice versa, maybe not so much stress, although you will have a few layers which will not be very crystalline, they will be a bit disorganized, but eventually, I mean, after a few atomic layers, the new lattice constant more or less prevails, and the rest of the layer is a nice crystal. So all of these are possible. They have advantages and disadvantages and so on, which we will not discuss here. But these are things that you have to bear in mind, especially if you will do some crystal growth, which you might do at some point, depending on your career path. So this is something to bear in mind. And I mean, that's more or less all I wanted to talk about. So I just wanted to give you a feeling for what the procedures or the techniques to grow crystals, to make all these devices that we have discussed in the previous lectures, that come from semiconductors or the very basic semiconductor physics, into the idea of making joints, and with the joints you can make transistors, diodes, and so on. And now really was thinking a little bit about the practical aspects, so how to actually make these devices. And I hope I convinced you that these devices can be made. And of course there are groups here that work on these topics, and you can find more information, of course, as well on the growth techniques and so on. And I would just leave you with that for the moment. So thank you very much for listening, and I'll see you next time.